Dear children, last class we studied about the effect of intensity of light on photocurrent, effect of potential on photocurrent, and effect of frequency on the photocurrent and the stopping potential, etc. So here now the topic is variation of stopping potential with frequency of incident radiation. So the last class we studied that when the frequency increases, then the stopping potential also increases, which means that when the frequency of the incident radiation increases, energy of that incident radiation increases. So we have to give more potential to stop the electrons. So we can say that the stopping potential and the frequency of incident radiation is directly proportional to each other. So when you plot a graph between these two, we get a straight line like this. So here the graph represents the variation of stopping potential and frequency for the two different metals. So here the graph represents, our graph reveals that V0 increases linearly with frequency. Okay, stopping potential increases linearly with the frequency of incident radiation for a given photosensitive material. When you take the metal A, then the frequency of the incident radiation on the metal A increases, then the stopping potential also increases. So we get a straight line. So when you consider the metal B, here also when the frequency of the incident radiation increases, then the stopping potential also increases. And there exists a minimum frequency, that is the nu zero. So for the metal A, this is the nu zero. So below that minimum frequency, the stopping potential is zero. Okay, the stopping potential is zero. That frequency is known as the minimum frequency, that is known as the threshold frequency. So below that frequency, the photoelectric emission stops, isn't it? So there exists a certain minimum frequency for which the stopping potential is zero, below which the photoelectric emission stops. This frequency is known as the threshold frequency. So we can say that there should be a minimum frequency for the incident radiation. Otherwise, the photoelectric emission does not take place. Then the photocurrent also stops. So the minimum frequency for which the photoelectric emission stops, that is known as the threshold frequency. So below that threshold frequency, no photoelectric emission is there and the photocurrent stops. Clear? So that minimum frequency is known as the threshold frequency, which means that there needs a minimum frequency for the incident radiation for the emission of photoelectrons. Okay, that means they need a minimum energy to emit. The electrons on the metal surface need a minimum energy to emit from the metal surface. Clear? And one more point is there, for two different metals A and B, the graphs are the parallel straight lines. So when you take different metals, or when you take the stopping potential and frequency for the different metals, we get the straight lines, parallel straight lines, and that is they have the same slope also, and but the threshold frequencies are different for different metals. Okay, threshold frequencies are different for the different metals because each metal needs different energy to emit the electrons from the metal surface. Okay, that is the nature of the metal surface is different. So they need different energy to emit electron from the metal surface. So the minimum frequency is different for different metals. That is the threshold frequencies are different for the two metals. So what is the threshold frequency? The minimum value of frequency of incident radiation below which the photoelectric emission stops altogether is called threshold frequency. Okay, and below which no photocurrent emits. Okay, that is no photocurrent is there. That frequency is known as the threshold frequency. And some other points are there. Once the frequency of incident radiation exceeds the threshold frequency, then the photoelectric emission starts instantaneously, even if the light is very dim. Clear? So Then the time interval between the incidence of radiation and the emission of electron is very very small, that is of the order of some 10 raised to minus 9 seconds, that is some nanoseconds, which means that the emission of photoelectron is instantaneously. It needs very less time. Okay, instantaneous process. It is an instantaneous process. So these are the points related to the photoelectric emission. Clear? Laws of photoelectric emission. On the basis of the experimental result on the photoelectric current, Leonard and Millikan gave the following laws of photoelectric emission. First point, for a given photosensitive material and frequency of incident radiation, the photoelectric current is directly proportional to the intensity of light. The saturation current is directly proportional to the intensity of incident radiation. So this point gives that photoelectric current is directly proportional to the intensity of light. Second point, for a given photosensitive material, there exists a certain minimum cutoff frequency below which no photoelectrons are emitted, howsoever high is the intensity of incident radiation. This frequency is called the threshold frequency. So which means that whatever may be the intensity of incident radiation, if it is very high, there should be a minimum cutoff frequency below which no photoelectrons are emitted. So that frequency is known as the threshold frequency. Then third point, above the threshold frequency, the stopping potential or equivalently the maximum kinetic energy of the photoelectrons is directly proportional to the frequency of incident radiation but is independent of intensity. That means threshold frequency, that is above the threshold frequency, stopping potential or the kinetic energy of the photoelectron is directly proportional to frequency, but it is independent of the intensity. Clear? Then the fourth point, photoelectric emission is an instantaneous process. The time lag between the incidence of light radiation and the emission of photoelectrons is very small, even less than 10 raised to minus 9 seconds. So these points are the laws of photoelectric emission. Failure of classical wave theory. According to wave theory, light is an electromagnetic wave consisting of electric and magnetic fields with continuous distribution of energy. This wave picture of light could not explain the basic features of light. So the first point is, according to the wave theory, when a wavefront of light strikes a metal surface, the free electrons at the surface absorb radiant energy continuously. Greater the intensity of incident radiation, greater are the amplitudes of electric and magnetic fields. Hence, higher intensity should liberate photoelectrons with greater kinetic energy. But this is contrary to the experimental result that the maximum kinetic energy of photoelectrons does not depend on the intensity of incident radiation. So here, wave theory explains that if the waves has greater amplitudes, it has greater intensity. So that incident radiation which has the greater intensity should liberate photoelectrons with greater kinetic energy. But this is contrary. That means this is against the experimental result of photoelectric effect. What does the photoelectric effect says? It says that maximum kinetic energy of photoelectrons does not depend on the intensity of incident radiation. It only depends on the frequency of incident radiation. Clear? Then second point, no matter what the frequency of incident radiation is, a light wave of sufficient intensity should be able to impart enough energy required to eject electrons from the metal surface. Thus, the wave theory fails to explain the existence of threshold frequency. So, according to the wave theory, whatever may be the frequency, the ejected electrons depends on the incident radiation. Okay. So, because of this reason, the wave theory fails to explain the threshold frequency. According to the photoelectric effect, the kinetic energy of the ejected electrons depends only on the frequency. Then below a particular, that means a minimum frequency, that is the threshold frequency, photoelectrons does not emit. That frequency is known as the threshold frequency. But here, according to the wave theory, says that the ejected electrons, the energy required to eject the electrons only depends on the intensity of the incident radiation. So, they cannot explain the threshold frequency. Clear? Then the third point, the energy of the light wave is smoothly and evenly distributed across its advancing wavefront. Each electron intercepts an insignificantly small amount of this energy, and so it should require a finite time to escape from the metal surface. But actually, the emission is almost instantaneous. So here, according to the wave theory, the energy of the light wave is smoothly. So each electron intercepts an insignificantly small amount of this energy. So each electron absorbs this energy continuously. So it should require a finite time to escape from the metal surface. But here photoelectric emission says that the emission is almost instantaneous. So in this way, wave theory could not explain the laws of photoelectric effect. Einstein's theory of photoelectric effect. After the wave theory in 1905, Einstein explained photoelectric effect on the basis of Planck's quantum theory, according to which a light radiation travels in the form of discrete photons. The energy of each photon is h nu. There are some main points related to this Einstein's theory. Number one, photoelectric emission is the result of interaction of two particles, one a photon of incident radiation and the other an electron of photosensitive metal. You know this. Then the second point, the minimum energy required to liberate an electron from the metal surface is called work function of the metal. So these points are similar to the experimental result of the photoelectric emission. Then the third point, each photon interacts with one electron. So that is shown in the figure. Each photon interacts with one electron. The energy h nu of the incident photon is used up in two parts. Then a part of this energy, a part of this h nu, a part of the energy of the photon is used in liberating the electron from the metal surface, which is equal to the work function of the metal. Then the remaining energy of the photon is used in imparting kinetic energy of the ejected electron. So each photon has an energy h nu. Then a part of energy is used to work function of the metal and a remaining energy is used in the form of kinetic energy, of the ejected electron. Then very few photons whose energies are greater than the work function are capable of ejecting the photoelectrons. So very few photons, whose energies are greater than the work function and they are capable of ejecting the photoelectrons. So by the law of conservation of energy, we can write energy of the incident photon, that is h nu. It is equal to h nu is given to the work function. Part of the energy is given to work function and remaining part is given to the kinetic energy. So we can write energy of the incident photon is equal to maximum kinetic energy of photoelectron plus work function. So we can write the equation h nu equal to half mv maximum square plus phi 0. So half mv maximum square, that is the kinetic energy of photoelectron, and phi 0 is the work function. So we can write K maximum equal to h nu minus phi 0, that is half mv maximum square, half mv square equal to h nu minus phi 0. That is the equation number 1. Then if nu, that means frequency is the threshold frequency. if frequency is the threshold frequency, then we can write the equation K maximum equal to h nu minus h nu 0. If the incident photon having the frequency, threshold frequency, then we can write the work function, that is the h nu 0. Okay, so K maximum equal to h into nu minus nu 0. These two equations are known as the Einstein's photoelectric equation. So the second equation represents that if frequency is the threshold frequency, then we can write K maximum equal to h into nu minus nu 0. So these two equations are known as the Einstein's photoelectric equations. Explanation of photoelectric effect. Einstein explained the photoelectric effect. So the first one, explanation of effect of intensity. So the increase of intensity means the increase in the number of photons striking the metal surface per unit time. As each photon ejects only one electron, so the number of ejected photoelectrons increases with increase in intensity of incident radiation. So this is same as the experimental result of photoelectric effect. That is, when the intensity increases, then the number of photoelectrons ejected also increases. Then the second point, explanation of threshold frequency. So in the above equation, if nu less than nu 0, okay, nu less than nu 0, then what is the kinetic energy? It becomes negative. So it has, that is kinetic energy negative means it has no physical meaning. So photoelectric emission does not occur below threshold frequency. Okay, photoelectric emission does not occur below photoelectric, that means it does not occur below the threshold frequency. Once again, if nu less than nu 0, that is the frequency of incident radiation is less than the threshold frequency, the kinetic energy of photoelectrons becomes negative. This has no physical meaning, so photoelectric emission does not occur below the threshold frequency. Then the third point, explanation of kinetic energy. If nu greater than nu 0, then K maximum is proportional to nu, that is above the threshold frequency. The maximum kinetic energy of the electrons increases linearly with the frequency of incident radiation. So kinetic energy, when the frequency of incident radiation increases, kinetic energy of the electrons increases. So moreover, the increase in intensity increases only the number of incident photons and not their energy. Okay, so increase in intensity increases the number of incident photons. It does not depend on their energy. Hence, the maximum kinetic energy of photoelectrons is independent of intensity of incident radiation. Then the fourth point, explanation of time lag. Photoelectric emission is the result of an elastic collision between a photon and an electron. Thus, the absorption of energy from a photon by a free electron inside the metal is a single event which involves transfer of energy in one lump instead of the continuous absorption of energy as in the wave theory of light. So wave theory explains that the energy is continuously absorbed by the ejected electron. But here, according to the photoelectric effect and the Einstein's explanation, it says that the transfer of energy is in one lump. Okay, so hence there is no time lag between the incidence of a photon and the emission of a photoelectron. It is an instantaneous process. Okay, so Einstein explains the photoelectric effect and the points are similar to the laws of photoelectric emission. Clear?